Hey everyone, and welcome back. We are on chapter 8 of our course. Chapter 8 is titled Network Segmentation, and it's very similar to what you would think when you think of segmenting something, blocking things off. It's kind of like a chef, like at a hibachi restaurant where they're slicing and dicing here. Think about segmentation as like organizing your messy garage, and it's labeled into zones. Okay. But instead of dad's old golf clubs and holiday decorations, we're organizing the network traffic. So that's kind of the gist of what this chapter is. So here we go. Now, and I will say that this chapter is kind of broken up into goofy sections, so I just want to make you aware of that. We'll be jumping around, but that's just because that's what the book does. So you may ask, why bother segmenting networks? So imagine throwing a party where you've got kindergartners, you've got teenagers, you've got your grandma's book club, and they're all in the same space. Be chaos, wouldn't it? So network segmentation is like giving each group their own room. When you split a network into smaller pieces, traffic stays separated, kind of like keeping the kids away from grandma's fine china. Each network becomes its own broadcast domain, which is just a fancy way of saying their messages stay in their own rooms. This helps with security, it helps with performance, and it makes troubleshooting way easier. Next slide, it says, this is really looking at how we divide things up with regards to segmentation. Common approaches include geographic locations, like separating your office in New York from your office in Tokyo. If you're thinking big, you can split it into departments, like keeping the spreadsheets for the accounting department away from the cat videos from the marketing team. Or you can divide it by device types, like IoT devices get in their own little corner where they can't accidentally take down your main servers. So it's kind of like organizing your kitchen. The plates go with other plates, forks go with forks, and then the weird gadgets you get for Christmas, you just throw it in the junk drawer. So, Operation Technology, which is shortened to OT, this is the stuff that actually controls the physical things, like factory robots or power plants or HVAC systems. OT is like the difference between your computer and your car's computer. OT systems love something called east west traffic, which flows horizontally between devices rather than up to the cloud. Problem is, this traffic is really hard to filter. Traditionally, companies kept OT completely separate from IT. It's like having two phone lines, one for business and one for personal. But now, with the industrial Internet of Things, everyone wants to connect to the internet. IT teams are nervous because suddenly the machine that controls the factory's temperature is one ransomware attack away from turning your workplace into a sauna. And even if we can't completely isolate OT anymore, we can still use logical segmentation, and we can put those into zones. Think of it like security checkpoints at an airport. There's the untrusted zone, which is like the wild, wild west of the internet. There's the trusted zone, and that's your secure internal internet or network. And then we got the screen subnet that sits in the middle like a bouncer, checking IDs. Micro segmentation takes this even further. It applies security to individual resources, like having a separate lock on every drawer in your house instead of just one lock on the front door. It's certainly overkill if you're thinking of it in terms of a house, but it's perfect if you want to protect your critical infrastructure. So we're going to take a look at storage area networks. They're basically a private highway built specifically for data storage. So imagine if your city built special roads that only delivery trucks could use. That's what a storage area network does for data. It separates storage from regular computing that connects them with high-speed links. Storage area network devices are like those massive warehouse systems that Amazon uses. They're designed to hold tons of stuff and make it available to lots of servers at once. If one connection fails, multipathing automatically reroutes it to another path, kind of like your GPS finding an alternate route when there's traffic. This also provides load balancing, so no single path gets overwhelmed. So it's kind of like infrastructure with a backup plan. Storage area networks use specialized networking technologies with names that sound like robot models. We've got the fiber channel. Um, we've got that over Ethernet as well, not to be confused with the ISCSI, which runs over regular IP networks, and InfiniBand, which sounds like a rock band, but it's actually super fast networking tech. The beauty of storage area networks is that you can put them in different building from your main network, which is good for data disaster recovery. They're also highly scalable. They're very fault tolerant and gives you massive storage with blazing fast access. Think of it like the difference between storing your stuff in your apartment versus having access to a climate controlled, ultra secure storage facility with instant delivery. Next, we're going to look at subnets. Imagine a business with just one big network. Everyone's on the same highway and one router handles all the traffic. That's like having one cash register at Walmart on a Black Friday. Not ideal. To improve things, we can segment the network so that each floor gets its own LAN or broadcast domain. But how do devices know who's on their floor versus someone else's? Yeah, that's where subnetting comes in. You divide your pool of IP addresses into groups, which is like sorting mail into different zip codes. This technique is appropriately called subnetting because we love straightforward names in network sometimes. So here's what a subnet looks like in practice. You've got one router connected to the internet and three switches connecting on the different floors. Before subnetting, everyone was in the same broadcast domain. Imagine anyone and everyone in the building shouting, "Is anyone there?" and hearing back from all 300 or 500 employees. That would be annoying. Subnetting fixes this by creating separate broadcast domains. Now, when floor 1 shouts, only floor 1 answers back, which is much better, obviously. The router acts like a switchboard operator and it manages traffic between floors when necessary. So, why bother with subnetting? Well, subnets make network documentation clearer. You know exactly where everything is. Problems become easier to locate and resolve because you can isolate issues to specific subnets, like knowing the plumbing problem is in the second floor bathroom, not somewhere in the building. Routers can manage non-overlapping IP addresses. Um, they're much more efficient on larger networks when IP addresses are mathematically related to the binary level. And the last one sounds complicated, but it is. But just know that organized numbers are easy to work with rather than random ones. Like how it's easier to find books in a library with the Dewey Decimal System, if you know what that is. If you don't, look it up. It's how we used to look up books from the library. Definitely easier to have a system than to just pile books up and then have you say good luck, find what you need. So a subnet mask is where it gets technical. Okay, every IPv4 address has two parts. It's got a network ID and a host ID. Think of it like a street address. The street name is the network ID and the house number is the host ID. A subnet mask helps devices figure out which is which. The mask is written in binary, ones and zeros, and the number of ones tells you how many bits belong to the network ID. For example, the IP address 192.168.123.132 In binary is a string of ones and zeros. The subnet mask 255.255.255.0 in binary is a bunch of ones followed by zeros. Where you see ones in the mask, that's your network ID, which was 192.168.123.0. The zeros indicate the host portion, which would be 0.0.0.132. It's like using a highlighter to mark which part of the address route matters for routing. So traditionally, IP addresses came in classes like economy, business, and first class, but for networks. Class A addresses start with 0 to 126 in the first octet and gave you 8 bits for the network, 24 for hosts, which are millions and millions of possible devices. Class B, which is 128 through 191, split it evenly, and it gives 16 bits for the network, 16 for hosts. Class C, which is 192 to 223, gives you 24 bits for network, only 8 for hosts, which is just 254 devices. This is called classful addressing, and it's about as flexible as airplane seating. Sometimes you need a few hundred addresses, not millions, and that's where classless addressing comes in. Subnetting throws out the rigid class system and lets you customize. This is called classless addressing. Here's the magic. You borrow bits that would normally identify hosts and use them for network information instead. It's like converting bedrooms into offices. You're repurposing space. By borrowing host bits, you increase the number of networks you can create, but decrease hosts per network. It's a trade-off. Want 4 small networks? Borrow 2 bits. Want 16 tiny networks? Borrow 4 bits. Each time you borrow bits, you double your networks, but cut your hosts per network in half. It's like slicing a pizza. More slices means smaller pieces. Class A, B, and C networks can all be subnetted, but each class has different amounts of host bits available to borrow. It's like having different sized pizzas to slice. The number of possible hosts and subnets varies based on your class and how you subnet. Thankfully, we have subnet mask tables to help us figure this out. Because honestly, who wants to calculate binary conversions all day? Not me. These tables are like cheat sheets that show you exactly what you get with each subnet mask. Network engineers keep these handy like a chef keeps their favorite recipes nearby. When calculating subnets, you need to figure out 5 key pieces of information. First, how many subnets do you need? Second, how many host addresses per subnet? Third, what's the network ID for each subnet? Fourth, what's the broadcast address for each subnet? And fifth, what's the range of usable IP addresses within each subnet? It's like planning a housing development. You need to know how many neighborhoods, how many houses per neighborhood, the neighborhood addresses, and which house numbers are available. The broadcast address is special. It's how you shout to everyone in that subnet at once. The process breaks down into 4 steps. First, borrow bits from the host portion. Second, determine your subnet mask based on these borrowed bits. Third, figure out the network IDs. These are your subnet addresses. Fourth, determine the ranges of IP addresses for hosts in each subnet. The broadcast address is always the last address in the range, right before the next subnet's network ID starts. Think of it like the last house on the street before you enter the next neighborhood. And here's an important rule. The broadcast address can't be assigned to any actual host. It's reserved for shouting to everyone, not for any individual device. So let's see this in action. Here we have a router connected to the internet and 3 switches, each serving a different floor with its own subnet. Each subnet gets its own default gateway. That's the router interface that connects to that particular subnet. Subnet 1 uses 192.168.89.0/27. Subnet 2 uses 192.168.89.32/27, and subnet 3 uses 192.168.89.64/27. That slash 27 notation is CIDR, which is classless interdomain routing, and it's shorthand for the subnet mask. It's like using NYC instead of writing out New York City every single time. The router has 3 different IP addresses, one for each subnet it connects to, acting as the default gateway for the devices on each floor. Now, here is a more complex example with one router connecting several LANs, each with its own subnet. Look at all those different network addresses. It's like an apartment complex where each floor has its own entrance. The router sits in the middle, managing traffic between all these different subnets. When a device in one subnet needs to talk to a device in another subnet, it sends the packet to its default gateway, which is the router, which then forwards it to the correct destination subnet. Without the router, the subnets can't talk to each other. It's kind of like needing an elevator to get between each floor. Next, we're going to look at a practical problem. It's expensive to create a DHCP server for every single subnet. So, how do devices on different subnets get IP addresses from one central DHCP server? The answer to that question is called UDP forwarding. UDP forwarding feature allows routers, firewalls, or other layer 3 switches to forward UDP broadcasts across broadcast domains. And here's how it works. A relay agent receives a DHCP request from a client on one subnet. It repackages the message with IP helper information and routes it to the DHCP server in a different broadcast domain. The DHCP server sees which interface the request came from and assigns an IP address on the appropriate subnet. It's like having a mail forwarding service. The DHCP request gets relabeled and sent to the right place. VLSM, which stands for Variable Length Subnet Mask, sounds intimidating, but it's just subnetting a subnet, which is like dividing an already divided pizza into even smaller slices. Why would you do that? Well, because sometimes you need different sized subnets. Maybe sales needs 50 addresses, but IT only needs 10. VLSM lets you create subnets of various sizes to match your actual needs, which minimizes wasted IP addresses. The trick is to start with your largest subnet first, then create the next largest, and so on. It's like packing a suitcase. Fit the big items in the bag first or the suitcase first, then fill in the gaps with smaller stuff. This way you use your IP address space much more efficiently than if every subnet had to be the same size. So here I want you to look at these diagrams. The top pie chart shows different department sizes. Sales is huge, accounting and HR are medium sized, IT and exec are tiny. The bottom chart shows how VLSM lets you create subnets that actually match these sizes instead of wasting addresses. Sales gets a /25 subnet with 125 usable addresses, while IT might only get /29 with 5 addresses. There's even unused space left over for future growth in this example. Without VLSM, you'd have to give everyone the same size subnet, which is like giving everyone at the buffet the same size plate, regardless of whether they're getting a salad or a full meal, which is a total waste. The good news is that subnetting in IPv6 is actually simpler than IPv4. First, IPv6 has no classes, so we're not stuck with that rigid system. Second, it doesn't use subnet masks. Instead, it uses prefix notation. Third, a single IPv6 subnet can supply over 18 quintillion addresses. Quintillion. So you got million, billion, trillion, quadrillion, quintillion addresses. That's an 18 followed by 18 zeros. You could give every atom in your body an IP address and still have plenty left over. Hopefully that puts it into perspective. The sheer volume of addressing means that we subnet IPv6 mostly for organization and management, not because we're running out of addresses, but it's like having an infinite supply of house numbers. You still organize them into streets and neighborhoods to make sense of them. An IPv6 address is written as 8 blocks of 4 hexadecimal characters. It breaks down like this. The last 4 blocks identify the specific interface or device, like a house number. The first 4 blocks identify the network, like the neighborhood and the street name. This is called the network prefix, site prefix, or global routing prefix. The fourth hexadecimal block can be altered to create subnets, giving you 65,536 possible subnets from a single IPv6 prefix. It's like having a city where you can create 65,000 different neighborhoods, each capable of housing quintillions of residents. We're not running out of space anytime soon. A couple of diagrams that show how IPv6 addresses are structured. The top shows the network prefix and the interface ID separated clearly. The bottom shows the hierarchy. First comes the RIR allocation, which is like a regional zone, then ISP space, then large organization space, and smaller organization space. Then finally, the interface ID for the individual devices at the /128 level. Each /64 subnet provides those 18 quintillion addresses we mentioned. The notation works like this. For example, 2608 colon 5E10 colon 1 colon AA/64. Now, that means that the first 64 bits are the network portion. The rest identifies the hosts. It's kind of like a super detailed address system where you specify in this example what continent you're on, what country you're on, what region you're in, what city you're in, what neighborhood, what street, and what house number, all in one address. Okay, switching gears like we've already done 47 times this chapter. We're looking at VLANs. VLAN is a virtual local area network that groups ports on a switch, so some traffic has to go through a router, even if devices are on the same physical switch. Why would you do this? Well, maybe you want to prioritize certain devices' traffic, like giving voice IP phones priority over someone streaming Netflix, or maybe you want to isolate heavy traffic patterns so they don't bog down the whole network, or separate devices that use old creaky protocols, or give certain users special security or functions for the network. VLANs are also great for temporary networks, like setting up for maybe a conference. They also reduce equipment costs because you can logically separate networks without buying more physical switches. So, looking at a diagram of a simple VLAN, one physical switch connected to a router, but logically divided into a manufacturing VLAN and an administrative VLAN, as you see they're highlighted in yellow and green. Even though they're all plugged into the same switch, the devices in the manufacturing can't directly talk to the devices in administrative without going through the router first. It's like having roommates who are forbidden from talking to each other except through text messages that go through you first. It's kind of awkward in real life, but it's useful for network security. The router acts as the gatekeeper, allowing you to filter traffic between the VLANs, enforce security policies, and keep sensitive data separated. VLANs only work on managed switches you can configure through a command line interface or web GUI. Unmanaged switches are like automatic cars, simple, but you can't control much. Managed switches are like manual transmission with all the bells and whistles. To create VLANs, you partition the switch's ports into groups. The switch handles this by working with layer 2 information, which is the data link layer, dealing with MAC addresses and Ethernet frames. By sorting traffic based on this information, VLANs create multiple broadcast domains from a single physical switch. It's like creating separate apartments inside one building, same structure, different living spaces with soundproof walls. The top image shows a managed switch with ports configured for different VLANs. They're kind of small, but can you see the labels? It says VLAN 2 for voice, VLAN 10 for accounting, VLAN 20 for marketing, and VLAN 30 for sales. Each group of ports is logically separated even though they're on the same physical device. The bottom diagram shows how this looks in practice. Computer A in VLAN 1 sends traffic to the router. Computer B in VLAN 2 sends different traffic. Even though they're connected to the same switch, their broadcasts don't interfere with each other. The router manages communication between VLANs when necessary. Think of it like having different phone lines on the same phone system. You can call within your line or transfer to another line through the operator. So, how does the switch know which VLAN a frame belongs to? It adds a tag to the Ethernet header identifying which port the message came from. This tag travels with the transmission until it reaches either the destination switch port, um, if the device is on the same network, or a router if it needs to go to a different switch or VLAN. It's like putting a luggage tag on your suitcase. The tag travels with the bag until it reaches the final destination. If the frame is being routed to a new VLAN, the router adds a new tag, like your bag getting a new tag when you transfer to a connecting flight. This tagging system is how VLANs maintain separation while sharing physical infrastructure. So this is another diagram. The question is, what if you need the same VLAN across multiple switches? This diagram shows three switches on a LAN with multiple VLANs. Notice in the slide that VLAN 1 appears on both switch A and switch B. That's the power of VLANs. They're logical, they're not physical, and they can span multiple switches. The connections between the switches and to the router carry traffic for multiple VLANs simultaneously. It's like having buses that pick up passengers from different neighborhoods at different stops, all sharing the same road. Devices on the same VLAN can communicate directly, even if they're connected to different switches, while devices on different VLANs need to go through the router regardless of which switch they are on. So let's talk about how multi VLAN connections between switches actually work. Each port is configured as either an access port or a trunk port. Access ports connect to end devices like computers or printers. They carry traffic for only one VLAN. Trunk ports connect to other network devices like switches or routers and can carry traffic for multiple VLANs simultaneously. It's like the difference between a residential street, that's the access port, that only serves one neighborhood, and a highway, which is the trunk port, that carries traffic from many neighborhoods. Trunking protocols manage the VLANs and Ethernet frames. The most popular is Cisco's VTP, VLAN Trunking Protocol, which coordinates VLAN information across all of your switches. This diagram shows how trunk ports carry multiple VLANs. The connections between switches and from switches to the router are trunk lines, and those are shown with dashed lines. These trunk lines carry tag traffic for VLAN 1, VLAN 2, VLAN 3 all at once, like a multi-lane highway where each lane represents a different VLAN. The access ports connect to end devices and only carry untagged traffic for their specific VLAN, like exit ramps that only go to one neighborhood. When traffic arrives at a trunk port, the switch reads the VLAN tag, knows exactly which VLAN that traffic belongs to, and then it forwards it appropriately. It's a sophisticated traffic management system that keeps everything organized. So here's what VLANs and subnets. Here's where VLANs and subnets kind of come together. Um, each each VLAN gets its own subnet of IP addresses. They're like peanut butter and jelly, two different things that work great together. The diagram here shows three subnets connected to a single router interface through trunk connections. From the router's perspective, it sees three logical LANs, all arriving through one physical port. Each VLAN subnet combination acts like a separate network with each its own IP address range and its own broadcast domain. It's like having three different office buildings all sharing the same driveway. They're separate spaces, but they share one connection to the street, the router interface. This diagram shows the big picture. We've got three VLANs or subnets connected to a router with trunk links in between switches labeled as subnet 1, 2, and 3. Each subnet has its own address range, its own broadcast domain, and its own set of devices, but they all connect through the same router interface using trunk connections. The router needs only one physical interface to manage the traffic for all three subnets, which is much more efficient than dedicating a separate interface to each one. It's like having one secretary managing calls for three different department stores instead of hiring three separate receptionists. So here's a cool trick. If you have a layer 3 switch, one that can handle IP routing, you can create virtual interfaces right on the switch. These are called SVIs, switch virtual interfaces or switched virtual interfaces. Switch or switched. Because we love acronyms in IT, obviously, we've had 1,000 of them so far. An SVI acts like a mini router interface that's built into the switch. If you create an SVI for each VLAN, the switch can handle inter-VLAN routing by itself without sending traffic to an external router. It's like having a building manager who can solve problems between floors instead of calling the landlord every time. This reduces traffic load on your router and it can improve performance since traffic doesn't have to leave the switch to be routed. So here's a diagram that shows a layer 3 switch with three SVIs, one for each VLAN. When a device in VLAN 10 needs to talk to a device in VLAN 20, the switch handles the routing internally through its SVIs instead of sending the traffic out on an external router. The message arrives at switch C, gets routed through the appropriate SVI, and continues to its destination VLAN, all without leaving the switch. It's like having an elevator inside your building instead of having to exit the building, walk around to the other entrance, and come back in. It's much, much faster. This works great for inter-VLAN traffic, but you'll still need a router for traffic going to other networks or to the internet. Not all VLANs are created equal. There are several different types of VLANs, and each of them have a specific purpose. So we're going to look at them quickly. The default VLAN is pre-configured on your switch and initially includes all the ports, like the factory settings. The native VLAN receives all untagged frames from untagged ports. Think of this one as kind of the catch-all. A data VLAN or user VLAN carries actual user-generated traffic like emails and web browsing. That's kind of like the main highway. A management VLAN provides administrative access to the switch, which is like a secure backdoor for IT staff only. And a voice VLAN is optimized for voice IP traffic, giving phone calls priority over other data. It's like having express lanes, regular lanes, emergency lanes, special lanes for ambulances, all in the same road system. And it's very hard to see, but there's a graphic there. And once you create VLANs, you maintain them through switch software. The image shows the output of the show VLAN command on a Cisco switch. Looks small, looks intimidating, but it's just a list of every VLAN on the switch, which ports belong to each VLAN, and a configuration, and all the configuration details. Think of this as kind of like a diary of the switch, telling you everything about how it's organized. Good documentation is critical because VLAN configurations can get complex really, really fast. You need to track which ports are access points, or access ports, which are trunks, and which VLAN each port belongs to, and also how VLANs map to subnets. So it's kind of like having to manage a complex filing system. You need good labels and organization, or you're never going to find anything. Now, common VLAN configuration errors include incorrect VLAN assignments. Maybe you accidentally put the HR director's computer on the guest Wi-Fi VLAN. That would be kind of awkward. Incorrect port mode. If you configure a port connected to a computer as a trunk port instead of an access port, that computer probably won't be able to communicate. It's like trying to fit a square peg in a round hole. And then there's VLAN isolation. If you accidentally isolate a VLAN from the router, you've cut that entire group off from the rest of the network, which is like locking a department in their office wing with no key to get out. So they happen, those mistakes happen, but if you have good documentation and careful configuration, you can prevent those problems. So, VLAN security. VLAN hopping is an attack where someone generates transmissions that appear to belong to a protected VLAN, then crosses VLANs to access sensitive data or inject malware. It's like sneaking into a VIP area by wearing the right wristband. There are two approaches. Double tagging involves adding two VLAN tags to a frame so it gets forwarded to an unintended VLAN. Switch spoofing tricks the switch into thinking an attacker's computer is actually another switch, causing the switch port to become a trunk port that carries traffic for all VLANs. Both are serious security issues. You need to protect against them properly by configuring trunk ports properly, disabling unused ports, and not using the default VLAN for sensitive data. Okay, time for VXLAN, which is Virtual Extensible LAN. Large networks often have multiple data centers interconnect. VXLAN creates a layer 2 network, which is the Ethernet, that overlays a layer 3 network, which is your IP, kind of like building a virtual tunnel system over existing roads. Messages get encapsulated in a VXLAN tagged header that includes information from layers 2, 3, and 4 all at once. It's like having a triple sealed package. Because of the extra packaging, networks supporting VXLANs need a larger maximum transmission unit, like 1600 bytes instead of the standard 1500 bytes. Um, think of it like needing a bigger mailbox to handle thicker envelopes. VXLAN is crucial for modern cloud data centers where you need flexible, scalable network virtualization. We're getting close to the end here. Now we're going to look at some cloud networking. We have a virtual private cloud, which is a VPC. It is your own private software defined section of a larger cloud network. It's like renting an office floor in a skyscraper and being able to arrange the walls however you want. In a VPC, you can typically configure subnets, load balancers, gateways, security controls, and tons of other network functions without touching any physical hardware. Everything is software defined and managed through a web console or an API. It's incredibly flexible. You can spin up new subnets in seconds, modify security rules on the fly, and you can scale up resources up or down as needed. Think of it as having a network made of Legos that you can reassemble instantly instead of concrete walls you would need like construction people to modify. So segmentation is critical for cloud security. In AWS, a VPC can contain two types of subnets. We have private subnets. Um, they host resources that shouldn't directly be accessible from the internet, like databases containing customer information. Public subnets host resources that need internet access, like web servers serving your website. Public subnets are associated with Internet Gateway, which is like having a front door that opens to the street. Private subnets don't have direct internet access, but they can communicate indirectly through a NAT gateway, which is a network address translation gateway. The gateway sits in the public subnet and acts like a courier service. It fetches stuff from the internet on behalf of the private subnet while keeping those private resources hidden. It's kind of like having someone shop for you so you don't have to leave your house, which got pretty popular during COVID. This diagram shows how it all connects. You've got a VPC containing both a private subnet and a public subnet. The private subnet has a database server that needs to stay private. The public subnet contains a NAT gateway. The NAT gateway connects through the internet gateway to the outside internet. When the database server needs to download updates from the internet, it sends requests to the NAT gateway, which fetches the data, sends it back. The database server never directly touches the internet. All requests are handled by the NAT gateway, which acts like a middleman that protects everything. Meanwhile, the public subnet can host things like web servers that need direct internet access. It's all about layers of security and controlled access. Finally, let's talk about edge computing. Latency, which is that annoying delay, can be reduced by locating cloud resources physically closer to users. But many customers are in places without nearby cloud data centers, either CDNs or edge computing, and a CDN is a content delivery network. They deliver or distribute copies of your data to locations worldwide, so users always have access to a nearby server. It's like having local convenience stores instead of everyone driving to one central warehouse. Edge computing takes us a little bit further by running actual computing resources on edge devices closer to users, not just storing static content. Think of this like moving from just having distributed warehouses to having distributed factories. This dramatically reduces latency for things like video streaming, gaming, and IoT applications. Your Netflix stream isn't coming from one massive data center in California, it's coming from a local CDN server, maybe just a few miles away. Take a deep breath. So, we have covered network segmentation, 42 minutes. We covered security performance. We covered easier management of it. We learned how to apply subnetting to network devices, carving up IP addresses, the space for them. We configured VLANs to create logical network separations on physical switches. And we explored networking and segmentation options in the cloud, including VPCs, subnets, and edge computing. Remember, segmentation is like organizing your house into rooms. It takes effort up front, but it makes everything run smoother. I appreciate you sticking with me through all these networks, within networks, within networks, within networks. Now, go forth and segment responsibly. That's a wrap for chapter 8. We will see you for chapter 9.